Well, greetings, Mr. Kolazar's class. We're going to start into section 4-2 on the atom. We're going to look at defining the atom today. We're going to look at differences between the subatomic particles and their relative charge and relative mass. And we're going to start describing the structure of the atom, including the location of these subatomic particles. So to begin with, the atom is the basic unit of matter. It's going to be the smallest matter, or the smallest division of matter that still has the chemical properties of that whole. There are 118 different elements on the periodic table. We'll see PT abbreviation a lot of times for periodic table. Of these, we can't ever actually see an atom. Atoms are too small to be seen with a regular eye or microscope. We can detect them with a scanning electron tunneling microscope or an atomic force microscope. And instead of actually seeing them with a detection, if we were to give an instrument, it'd be basically almost like Braille, where you can feel over the top the repulsion forces of one atom and the repulsion forces of the electron cloud of another atom, and we can map out around the sides of where each force is actually felt at, and we can process that into art and images, but we can't actually determine what the atom actually looks like. So an example here that I've actually set up and actually shown our atoms lined up and how they actually may or may not look with the artist's representations of the colors and images. IBM a long time ago actually set up a bunch of nickel atoms, I believe, and put them on one plate and actually wrote out their logo one atom at a time. And what we're seeing here is the electron forces of the outside of the atom is what's actually being measured or represented there. And this one's really nice. If you can read this, you are too close, and extremely too close there, if you could actually look at the atoms. Now, there are three parts of the atom that you need to know. And the chart begins at the bottom of that second page, number 2 of the chart, the proton, the neutron, and electron. And these are going to be must-knows for the rest of this time. Now, there are three parts to the atom, and just to give a little credit, J.J. Thomson came up with the cathode ray experiment, and the cathode rays, particles that are negatively charged, the electrons have a partial negative charge and have very little mass. And he set up a negative and a positive tube and actually had those negative electrons attracted to the positive end of that source to show the electron as part of the atom. From there, Ernest Rutherford, gold foil experiment we're going to talk about in class. Rutherford came up with the idea of there's a nucleus and it's contained with protons, and they're going to have what we're going to know is a positive charge. So he determined that the atoms have a dense core that's positive, known as the nucleus, and that the protons have a positive charge. So protons and positive are going to go together. And our last one, neutron, was discovered by James Chadwick. He did some radioactive experiments in order to determine the neutron. So this chart must know, must know, must know. Hint, you must know this chart. So as we look through the proton, discovered by Rutherford using the gold foil experiment, the symbol for proton, instead of writing out the word proton every time, is a lowercase p with a little plus sign to it. So P positive for proton. It's located in the nucleus. We're going to give it a charge that's positive. We're going to associate with a number, so every proton has a positive 1 charge. Relative mass, we're going to talk about this as we're going, is our atomic mass units, or AMUs. We're going to give that an atomic mass unit of 1, because the actual mass in grams of a proton is 1.67 times 10 to the negative 24th, and that's going to be a very small number. We can't actually measure that out, so we relate that relative mass to being 1. Now for neutrons, Chadwick, radioactive experiments, symbol for neutrons is just the letter N. They're also located in the nucleus. The charge of a neutron is neutral. There's no charge, so it's 0. Relative atomic mass, AMUs, also at 1. They're very close to the mass of the proton. Basically the same, so they're both given the mass of 1. And last one, the electron J.J. Thomson with our cathode ray tubes. Electron's charge, our extremity symbol, E minus. It's found in the electron cloud outside of the nucleus. Its charge has a relative charge, or charge of -1. Relative mass, 1/1840th of the mass of the proton-neutron. Basically, it amounts to approximately 0 if we think about it. It does have some mass, relatively speaking, but we're not going to include it in the overall mass of the atom. So this chart is a must-know chart. It's something that we're going to see throughout the year describing those parts of the atom. Now, the atom itself, this is just a model representation. Inside is where the protons and neutrons are. That's the nucleus. It's very dense. Protons and neutrons are located there, meaning 99.7%, 99.97% of the mass is located very close to the center. They're kind of spherical in shape, but that shape will change as we're going. The electron cloud is the space outside where these fast-moving electrons would be located. And they're just going to be zipping around, zipping around, zipping around. Somewhere outside of the nucleus is where they're going to be. And as they move around that outside of the nucleus, this is going to be the forces of repulsion that we can actually see or detect from one atom to the next. And that's going to be where most of the chemistry happens at, is in that electron cloud. So atoms spherical in shape. Most of the atom's volume is empty space, that electron cloud. Most of the mass of the nucleus, our atom's mass, is located in the nucleus, and electrons are constantly moving, and they're held around the nucleus because of their attractive pull or force to the positively charged nucleus from the protons. Now, if we were to compare the size of the atom to the size of the nucleus, the size of the nucleus is very small, but it has almost all of the mass. Now, the electrons in the electron cloud outside take up a large space, but almost no mass. If we were to compare, where the nucleus is to where that electron cloud is, where the electrons would be electrons out here, protons and neutrons in here, the nucleus, if it was the size of a marble, let's say that was the size of an actual marble, the electron cloud of where the electrons could actually be orbiting around would be about the size of the Fargo Dome and most of the Fargo Dome parking lot. So when we compare the nucleus to the electron cloud, we can see that most of the atom is empty space, where that electrons are cruising around in with a very dense center and then mostly empty space there. So that's just a crazy comparison when we think about the atoms and everything that make us up are mostly empty space.